Okay, so we're back on the MATLAB EEG lab calculation of ICA components, which hopefully will make a lot more sense to you once we open up the file and I show you what that actually is. You'll notice that this took 282 iterative steps. Notice now that they then begin to scale components and they then sort of renormalize everything. So what the algorithm does is it makes sure that you have the same power in the signal before and after the process. So anyway, 282 steps, and that took approximately 15 minutes on my computer, which has pretty good RAM. But it is a laptop. It is 3 years old. I'm working with a MacBook Pro. So you will need a reasonably fast and good computer. Close as many windows as possible. As you saw, it was going very slowly for us because I was also running a background screen record and that was taking some time. So anyway, you can see that we did have, we are done now. Notice on the class demo filtered our file that we've been working on, and we did work from the one where we did not eliminate any of the noise components. Notice that we have a new data set. I mean, we don't have a new data set, but what has changed is this ICA weights. It was no, now it's yes. So that's just telling me that in the data set with this name, I will now have independent component analysis has been run. And if I save this now as a file, and by the way to do that is you can save the current data set. So you can save the current data set. When you save it, it will create two files. It'll create a .set and a .fdt. To reload those, you will no longer need to do import data. Once you've imported it into EEGLAB and you save the data set, it's going to save it as a .set and a .fdt. Both of those will need to be in the folder, but from this point on, all you have to do, you will not have to import data, you'll only have to load the existing data set. All right, well, back to this. So now let's go to the plot command, and let's look at component activations. So what this has done is it has done this transformation, this transformation that takes you from channels to sources. So if you have up to 65 channels, it will give you a model of 65 potential sources. Not all of those are unique sources, but the way independent component analysis is, what it does is it looks for sort of minimum variance. So in other words, you're looking for the components of the signal that are the least Gaussian or the least probabilistic. So let's just pull it up so that you can see what that looks like. So what it's now plotting is it's no longer plotting channels, it's now plotting components. And so what I want you to note, and it's a little bit hard on this scale, so I'm going to reduce the vertical scale a little bit. And so notice first of all this bad spot at about 4.5 seconds. It is still spread out over several channels. So this illustrates the point that I want to make, that you probably wanted to get rid of that before you did the independent component analysis, because in a perfect world, what would happen on the independent component analysis is that would be isolated to a single component. Notice, for example, up here on component 1, and let me change the setting. Excuse me, let me change the setting where I display fewer channels. Let me display 25 channels or so that you can see clearly what is the difference between a channel that looks like an EEG channel and a channel that's clearly something else. So if we look here, you can see, let me reduce the magnitude pretty significantly on this. So you can see that you have like this kind of artifact it seems to be isolated to components 2, 3, 4. And then when we get down here, we're seeing what appears to be more like a standard EEG. So what the EEGLAB algorithm is going to do is it's going to isolate your non-EEG components into some of the ICA components. You might have one, this right here looks an awful lot like EMG and some sort of background drift. But as you go farther and farther down or up, depending on how you think of it, you see that these channels here look more like conventional EEG. And let's blow them up so that you can see what those look like. Yeah, these look actually like brain waves, whereas these in these top channels look a whole lot less like brain waves. So there's another way to view this. You can also plot component maps, and we'll plot them in 2D. All right, now what it's going to do is it's going to pull up a two-dimensional map of the head, and it's going to show me for that individual component where its energy is concentrated over the entire time frame of the data set. So I'm going to wait until this loads. It's kind of slow, and this is actually legitimately a slow process, but it certainly is slowed more by the fact that I am recording. Okay, now the red areas are the areas of sort of the highest signal intensity. And you see this one where we have like a signal focused in one dot. That is a highly improbable actual physiological signal within the brain. So what does a brain signal look more like? If you look here at channel 28, channel 38, really most of these channels, really from probably 26 and up, are the way it would look if you had a region of your brain. Say if we look at channel 40, this is your visual cortex here. Clearly it's active, and so channel 40, yeah, that's probably EEG. Channel 30, this is your right frontal lobe. Yeah, that's probably activity in the right frontal lobe. This is your left temporal. Yeah, probably activity in the left temporal. So what you're going to do is you're going to simultaneously, or this is what I do, I simultaneously look at these figures and my time domain components. And so right away, for example, if you look at channel 6, you see these crazy swings. You see this very atypical looking pattern. And if you look at channel 6 here on the two-dimensional topographic plotter where the power is, you can see the power there isn't even inside the head. This most likely indicates that you've got something on the right side of the face or in the right eye that's moving. Channel 5 is similar. There's this one very localized dot that would be very atypical of what a normal EEG pattern looks like. And if I come and I kind of track along channel 5, you can see it's just all over the map, kind of no pun intended there, but it's up and down, and you see a lot of just unusual activity in the time domain. So when I decide which components are due to artifacts or noise, I make the decision by looking at the time domain plot and the head plot. Now, there's no wrong way to do this, okay? So I'm just going to kind of walk you through kind of what, if we just, and we'll just look only at these plots. But I'm going to say that 1, 5, 6, 7, probably 9, and let's pick another one. Maybe 24. So what was it? 1, 5, 6, 7, 9, and 24. Okay, so now what we're going to do is we're going to come to Tools, and we're going to tell it we want to reject some data using ICA. And actually, no, let's go to remove components. This is a little bit easier. So we're going to remove some components. And now it's going to ask me, okay, what components do you want to remove from the data? So let's remove component 1. What did we say? 5, 6, 7, 9. And this is MATLAB syntax, so separation by, oh, sorry, that should be commas. 5, 6, 7, 9. And then we said, let's go ahead and say 15 and 24 and maybe 49, because that looks, see how that's kind of outside the head? A lot of times that is neck tension. So 15, actually, you know, I'm going to leave 15. Let's say 19, 24, because we're right up here on the eye, with just a really, you know, localized dot. So 19, 24, and 35. Now, as a general rule, they say you do not want to remove more than between 25 and 35% of your components. If you're starting to have to remove more than 25 or 30%, if you have to remove more than a third of your components, which in this case would be 20, then you're getting too much artifact and not enough signal. If you look down here while we're talking, I was thinking about maybe 47. Let me look at its time signature. Let's look at 47 and see if it looks weird compared to the other two, or compared to the others around it. So no, I actually don't see anything weird in 47. So if it's a gray area and I can't really tell, 35, I don't know if it was one of the ones that we decided to exclude. Yes, it was. And you see how it looks different? Sometimes I kind of test myself and I'll go pick the ones from the figure that look off, and I'll go and pick them from the time plot and see if I agree. Just as a way to kind of, I don't know, sometimes you get bored when you analyze all the details. All right, so we're going to tell it okay. And are we sure we want to remove these components? Yes. Okay, now notice that it's going to create a new data set and it's going to call it pruned with ICA. We will tell it okay. And now let's come see, we've got pruned with ICA. So basically what we did is we zeroed out those components that to us looked like components that weren't true EEGs. So now let's plot the channel data and let's see if it looks different. And truthfully, it doesn't really look as different as I would have hoped. We're still getting a lot of these eye movement type. It could be that maybe we should have removed, 2 and 3 and even 4. So let's see. I can't remember, to be honest, if it'll now allow me to remove more components. Let's see. Let's go ahead and remove 2, 3, and 4. And yes. Okay. And let's call this version 2. 2. Okay. And now let's plot again. Okay, and now notice, I've now made a significant difference. You note that these little plateau-like tabletop things are mostly gone. I still have this guy, he's a mess, but they're mostly gone. These guys are still hanging around a little bit, so probably I missed a component somewhere. So you're going to have to play around with this, trial and error a little bit, and see kind of, what the best technique is that gets rid of some of these things. Actually, I'm not terribly concerned about the ones that remain. It's not terrible. They're pretty spaced out. Um, I think, like I said, this one's maybe not great. But what you don't know that I know is I'm looking between the stimulus and the response, and I notice that this occurs after the response. So typically when I analyze these signals, I'll take from the stimulus about between half a second and a second. Once the person has answered the question or responded to the stimulus on the screen, it is not uncommon right after that to see eyes move. Because what they do is they relax a little bit. They maybe look down, they maybe blink, they maybe take a deep breath because they've paid attention, they've seen the stimulus, they've given their response, and then a lot of times they will relax. All right, so I'm pretty pleased with this one, the way it looks, and so I'm going to come here and I'm going to tell this to save the current data set. And I'll just save it as class demo filter. And then let's go. I understand that most of you don't have a Mac. Here we go. Okay, so notice it showed up as two files, classdemofilter.set and classdemofilter.fdt. You'll need both of those, and they'll need to be in your MATLAB directory if you should try to load these again into EEGLAB to do further work. Okay, I'm going to cut it off at this point on the video because these are difficult to process if they get too long, and I know they're also difficult to listen to. What we're going to do next, I'll probably have the video up in a day or so, is we're going to look at these markers and try and figure out if we want to start analyzing some data and making some comparisons. Now that we've got our data cleaned up a little bit, we might want to figure out sort of what is the best way to do this. All right, so let's stop the video, and you should have enough now to know how to load files into EEGLAB and do the preliminary processing.